This is an introduction to the concept of double integrals over a rectangular region. So we'll consider this arbitrary surface function, z is equal to f at x, y, and we want to look at the surface over some two-dimensional domain region in the floor, R, where the x values are going to go from a to b, the y values are going to go from c to d, and these constant values are going to give us a rectangular region in the floor. And ultimately, we're trying to find the volume between this region in the floor and the surface function. So we're developing a formula to approximate this volume. So we'll begin by dividing the interval from a to b into n subintervals. So let's consider one of these subintervals to have a width that we'll call a change in x. And the width of this subinterval is going to be determined by the terminal minus initial of those x values divided by the number of subintervals that there are. So each one is b minus a over n wide. Similarly, we'll divide that y interval into m subintervals. And these subintervals are of equal length, and we'll call one of them delta y, a change in y, and the width of each subinterval is d minus c divided by m. Now let's consider this subinterval in the direction of x and this one in the direction of y. And notice we get a small rectangle here in the floor. Let's let delta A represent the area of that tiny rectangle. And that delta A is going to be length times width, which is delta x, delta y. Now we can think about the four corners of this little tiny rectangle as flying up to the surface. Now, if delta x and delta y are sufficiently small, we can think about this as being a flat-topped rectangular solid. Now let's recall that the volume of a rectangular solid is going to be the area of the base multiplied through by the height. Now the height of this rectangular solid is going to be determined by the function value of the surface, or the output value, when we plug in some domain element that's inside this little tiny rectangle. Let's consider the domain element x sub I and y sub j, so that this corner of our rectangle is the ordered pair x sub I, y sub j. If we fly that corner up to our surface, we get the ordered triple x sub I, y sub j, and the function evaluated at x sub I, y sub j. And this z-coordinate is the height of this rectangular solid. So we can say the volume of this rectangular solid is going to be the function evaluated at x sub I, y sub j times delta A. So in order to talk about an approximation for the total volume, let's take a close look at this rectangular region in the two-dimensional floor, where x went from a to b and y went from c to d. We're basically considering the ith subinterval in the direction of x and the jth subinterval in the direction of y to get the rij rectangle in the floor, where x sub I and y sub j was the ordered pair that we flew up to the surface. So in order to approximate the total volume, we're basically going to add up infinitely many of these rectangular solids, starting with essentially the one in the corner. We're basically going to split this up into those n subintervals and split this up into those m subintervals in the direction of x and in the direction of y. So we begin by looking at our first corner, which is going to have a height determined by x sub 1, y sub 1, plugged into the surface function, multiplied by the area of the base, which is delta A, plus then we add the volume of the next rectangular solid, which is going to be determined by x sub 2. We're at the same y coordinate though. That's going to then be multiplied by delta A again. And we can keep going along this first row, all of them having the same y coordinate, so we'll say dot, 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 and we continue in this direction until we get to the nth x value. We're still with y sub 1. That is going to be multiplied by delta A, and we've added up all the volumes of that first row of rectangular solids. Plus, now we move on to the second row. The volume of this cylinder is going to be determined by still x sub 1, we're at the same x coordinate, but now y sub 2, we're at the next y value, times delta A. They all have the same area of the base. Our next corner is at the ordered pair x sub 2, y sub 2 now, times delta A, plus we keep going in this second y value row to get the volumes of all those rectangular solids until we get all the way out to x sub n y sub 2 times delta A. And we keep on adding up more and more of these rectangular solids until we get up to this top row where the height of the rectangle is determined by that first x value again, but this time we are at the mth y value times delta A, plus the function evaluated at x sub 2 y sub m delta A, plus continuing on down this row until we get to that last corner, which is x sub n y sub m delta A. So this is a lot to take in. Let's try to use some summation notation to simplify this. And we'll start by looking at each of these individual rows. So the pattern for the first row is that the subscript on the x is the thing that ticks away. So we'll say our first row is the sum as I goes from 1 to n of f at x sub I, but all the y values are y sub 1 in that row times delta A. So that's our row 1 summarized using summation notation. The second row has, again, those x subscripts are the changing value. So we have the sum as I goes from 1 to n. The x value subscript changes. The y subscript is y sub 2 in every single one of those, delta A. Plus, we'll do a little dot, dot, dot here to hold space for this row. And then we'll finally then get to the last row, which again, the x value subscript is what ticks away, and the y value subscript is always y sub m here. So we say the sum as y goes from 1 to n, x sub I, the thing that's changing, y sub m not changing, again, delta A. So now we're going to use summation notation again, and this time the thing that we are summing is a bunch of sums. So we've got, these are the template for the argument for another summation. So I'm going to use a blue sigma symbol to symbolize that we're summing these big blue boxes. And the pattern of what we are summing is another sum. They all have sum I goes from 1 to n. They all have x sub I in each of these expressions. The thing that changes here, though, is that y goes from 1 to 2 all the way up to m. And so we'll say on this blue summation that j starts at 1 and goes to m, and that is what changes in this argument, that j value. Everything else is the same with each of those summations. The only thing that changes is that j subscript. So let's clean this up just a tad bit more, eliminating the brackets, and we'll say that this is what we call a double Riemann sum, where j goes from 1 to m, I goes from 1 to n. The argument is f at x sub I, y sub j, delta A. And this is what we call, again, that double Riemann sum. Notice this is an approximation for the volume, and that's because we're adding up a bunch of rectangular solids. But if we were to let the number of rectangles go to infinity, this is where we get the exact volume underneath that surface. So let's say that this double integral is the notation that we're going to use to represent the exact volume, so we'll use a straight equal sign here. And that exact volume is determined by allowing these m's and n's to go to infinity, letting us have infinitely many rectangles that are infinitely small. And I think it's better to just say x sub I, y sub j here to match what we were just looking at. Now, notice that if we have all of these surface values above the xy plane, then the outputs of the function are positive, which would give us an overall positive volume. But if some of that surface is below the xy plane, or even mostly below the xy plane, we would end up with an integral yielding a negative value, and that just means that the volume of the surface is mostly under the plane, but it can still be considered a volume.